little bit about the things we started to talk about last time. So last time we were talking about how information from one source can be combined with information from another source to learn about the probability of one thing happening using information about the other thing to calibrate our understanding of that. So we're going to do a little bit of that today, and we have some tutorials, some R tutorials, since I know everyone here, when we've had that first class, everyone was saying we really want to learn R. R is something that we're eager to learn. So I think it's been working, at least from my perspective, reasonably well to start with R and then to move into more conceptual material. So the first part's almost like a review, but then some new things that then get further covered, further refined when we go through in the second part of the class. So I'll talk for about 35 or 40 minutes. Hopefully the tutorial doesn't take quite that long, but then we'll have a little break, and then we'll come back together and we'll talk again about probability, since we didn't cover it in the detail that we need to cover it. So that will be our mission for today. Any questions? Yeah, so the tutorials and the PDFs have been updated in Piazza, and this is on review, since we covered the material last time, but it's always good to rehash and review. So some of this is review, just going through, how there are these built-in functions in R for using PDFs, PMFs, and so forth. And so this is all just review here. For example, we could use this dbinom, code to calculate certain probabilities, or we could calculate CDFs using R as well, using this pbinom sort of function. So these are things that we've covered, and they're just here so that you get it again, just from another point of view, just another example, and you just see it in a different setting. So this is just that in a different setting. Andreas?
Do you think we could briefly talk about the difference between probability in PMFs and probability density in PDFs?
Yeah, do you want to?
It's on the y-axis on both of them.
Okay, do you want to cover it, or should I cover it? Okay, so okay. All right, there's a question in the field. Andres, our wonderful Andres, had a question, just clarifying for the group, for all of us, the difference between the difference between PDF and PMF, just again, since we kind of touched on it, but it's good to touch on things multiple times. And one way to think about this distinction is to go back to that example that we talked about before. So if X is normally distributed, let's just say with a mu of 2 and a standard deviation of 1, if this is what X was distributed according to, we could ask ourselves, what's the probability that X takes on the value little x? And remember, little x just gets replaced with something. So little x could be replaced with 1. And we could ask ourselves this question. Well, this random variable here is defined over not just a discrete set of possibilities, 1, 2, 3, 4, but now it's defined over a whole continuous set of possibilities. So that changes the game. There's a qualitative shift from that. When we go from things defined in a discrete space, like 1, 2, 3, 4, to things that are now defined in a continuous space, 2.77777778, 2.7777777779, and so forth and so on. So in the context of continuous spaces, because real numbers have sort of an infinite precision associated with them, the actual probability of any continuous random variable taking on any specific value is equal to 0. So for example, if we just used R, we could do d norm, I guess what would be? I guess there's not really a great way there's not a great way in R to show that, but the basic intuition is hopefully simple. Remember how we use CDFs to calculate, so the basic intuition is if you have, and I'm writing on the board for those who may be listening, I drew a bell curve, and remember how we used CDFs before to calculate the area within this space. We're going to do that again because I think it's good to see it a few times to really have it fully sink in. But the intuition behind this distinction between a PDF with a D and a PMF with an M is that when we're working in a continuous space, the probability of any specific realization is so small it actually turns out to be 0 because there's an infinite precision associated with all the numbers. So the probability that the random variable takes on any specific value is itself equal to 0. just because of the fact that there's that infinite precision, and you can always find a number that's a little bit bigger or a little bit smaller, and it's not quite right. So the fact that you can always add more precision to a real number, a number defined in some continuous domain, means that you can't just say, the probability of x, the probability that x equals 1 is just 0 when we have a random variable defined over this continuous space. This was different than a discrete space. So for example, in the case of the Poisson distribution, so if we have x is distributed according to a Poisson distribution with the lambda parameter equal to, let's say, 99.2, 99.1, in that case, x is now defined over, x has to live, so to use some late second notation now, x has to live within, all these numbers from 0 to positive infinity, but they're all integers. So there's a difference. Even though we have infinitely many possibilities that this random variable can take on, it could be 0, it could be 1, it could be 2, it could be 3, it could be 4, and so on and so on and so on. It's not defined how high it could be. There's still a qualitative difference between that situation and the situation when you have a continuous random variable where there are infinitely many possibilities between any possible value that it could take on and any other possible value that it could take on. And that kind of changes the game in some fundamental way. There's a qualitative shift from that quantitative shift, and that's why in the context of discrete random variables, so for discrete RVs, we think in terms of PMFs, probability mass function, where we can actually say the probability of x equaling x can actually be kind of written in some, we can actually say what that probability is, whereas in the context of continuous random variables, continuous RVs, now we don't think in terms of PMF, it's no longer M, it's now a D, because now we can't think about the probability mass associated with any possibility. Now it's a density. So we've shifted from mass, we've gone to density, and this captures the fact that the probability of any x equaling any specific value is equal to 0 within the context of continuous random variables. So there's a shift from one to the other, and it's due to the support that the distribution is defined over. The support can be kind of infinite in both cases, but there's a subtle shift in how the infinities work, which you can learn more about in some of the other classes that you might be taking. So there are actually different levels of infinity, and it's an interesting field of mathematics. The different characterizing, which kind of infinity is bigger than which other kind of infinity. So you can read more about that, and there are these arguments that you can go through and think about it. But we're not really doing a course on the different kinds of infinity, but we are talking about it because it's relevant here for illustrating the subtle distinction that Andres was asking about between the PDF and PMF, and that was a premiere. But did I miss anything? What are your thoughts?
No, I like that. I just wanted to emphasize that whenever you see the graphs of PMFs or PDFs, the y-axis is different, and that is still a little bit tricky to me. So the y-axis on PMF, so it is discrete, the y-axis is going to be a probability, but then for PDFs, so for continuous random variables, the y-axis is going to be a density. So you might see like a 0.3, for instance, on the y-axis, but it's not that the probability is 0.3, it's like density is 0.3. That's a relative measure.
Yeah, exactly. So when you see probability density, think about that in some intuitive sense, like the relative likelihood. It's not really a probability, but it's a relative, likelihood in some informal sense of one thing happening compared to another. So in the context of the bell curve, it looks like this. The y-axis, like Andres is saying, is density, meaning this thing that's higher is more likely than this thing that's lower, but the actual interpretation of these numbers can be, it's just different. So you can have densities that are greater than 1, but you can't have probabilities that are greater than 1. So that's one distinction there. Whereas with the PMFs, you can, a PMF, the value of at any entry in a PMF can never be greater than 1 because this y-axis here is probability, whereas here it's probability density. So that's just a subtle distinction which can be confusing if you see it for the first time. Any questions or follow-ups about that? Okay, sounds good. Very good, very good. So that's a bit there. And now this is just reviewing, CDFs. And this is going to be important later on when we talk about things like statistical power, statistical inference. the notion of a p-value is actually going to be very much connected with this notion of a CDF. So when you see CDF, don't just think it's this abstract thing that I'm never going to use. Think this is something that I'm going to use and think about every time I read an empirical paper within the social sciences. They're going to have a p-value, and that p-value is telling me something about probability under certain assumptions. And that's something we'll cover in the second half, or the second module of the course. What that means, what is this notion of statistical inference? So it's going to be big. It's going to be something that we'll all learn about together. So that's that. And just as a reminder, there are multiple ways to calculate the CDF. I'm going to show you one of them. So you could use the built-in R functions, and that's what this is. But if you wanted to dive deeper into your understanding and use some manual functions to actually compute the CDF in R, you could do that. So remember how the CDF was defined. So f of, you can write it in a few different ways, but f of x, this can be thought of as the CDF, and this is like the integral in the continuous case from negative infinity all the way up to x of the density of p of x. So this is, the interpretation is the probability of seeing an value of the random variable, as they're less than or equal to the value of little x. So this is kind of the interpretation of it, and we're basically saying, take the in the PMF case, it's a little bit simpler. Think about, if you're looking at this as x, you just take the probability that you were here, and then you add it up with the probability that you were here below x, and then you add it up with the probability that you were here at x. So you just take everything to the left, and you just add it up, add it up, add it up. But remember, in maybe math camp, we talked about it, how in the context of continuous, variables, continuous sorts of random variables, we can't just sum things up because there are these infinities that we have to deal with. There are infinitely many values from here to here because this is a real a distribution defined over the real line. So therefore, instead of just taking a sum here, sum here, sum here, we do exactly the same thing. We just do a sum here, sum here, sum here. But now those sums become infinitely kind of small, and we have infinitely many of them, and that sum turns into an integral. So it's a sum turning into an integral, and this is another way of characterizing the CDF, and that's something we'll talk about in the probability inference part of the course. But you might ask yourself, well, that's sort of abstract. Let me see it in practice. Let me see it actually done in R, because R is a way for making palpable things that might otherwise be hard to make palpable. So let's actually do this integration in R. So what are we actually going to do here? We're going to use this integrate function, this integrate command, and it's going to integrate one-dimensional functions. And we've used the question mark notation to learn about this R function. And now we're learning a little bit about it. There's a description here. The description is not essential for the purpose of the discussion right now, but it's just for your own edification. And basically, what we're going to do now is we're going to pass into this integrate function a function. So this is a subtle thing for some of you who are new to programming. The input to the function, one of the inputs, is a function. Because in an R, a function is just an object like any other. It's like characters in a story. You have the matrix, character, and then you have the function character, and you can work them together. So the input to this integrate function, one of them, this f, is a function. So this is the function that we're trying to integrate. So you can think of f here, which I'm highlighting as that's this p of x thing that we have here. So in this context, f is p of x. It's a little bit confusing, I know, but basically the function that we're integrating is this p of x function. So we literally just write the function. So f of x, and we just wrote a little function here. F of x, d norm x comma mean 0.2 standard deviation square root of 2. So this defines the density that we're going to integrate over to then get the CDF. And remember, the bounds of this integration, which is really just a sum done in some continuous way, the bounds of it go from negative infinity, like we had here, all the way up to x, where x here, the x that we're slotting in this setting is just equal to 2. So this is how we can use the integrate function to get the exact same thing that we would get using the pnorm command in R, which is a built-in function, but instead we use sort of a manual approach so that we could actually, at least in some other way, see how it was being performed, so that we could hopefully get at least some level of intuition for what was happening. Questions, comments? Yeah, I'm sure that there's something out there. There are questions. I know that there are questions, but what are your thoughts? What question do you have? Does this make sense? Yeah. Do people kind of get what line 38 to 41 is doing?
Can I ask about the absolute error?
Yeah, good question. Good question. So for those on the recording, so we perform this integration, and there is this absolute error associated with it. So we run it, and it gives us an absolute error less than 2.3 times 10 to the negative 6. So the question is, what is that? So the answer there is that there are several different kinds of integration. In one kind of integration, we can use the analytical formula derived by mathematicians to do the integration. So for example, we can literally go with the integral and we can compute it, the integral of f of x, and we can figure out what the analytical formula is, and that would be an exact solution. But in some cases, we don't know what the exact solution is. And in those cases, we use numerical integration, where we basically approximate the integral, but instead by basically slicing this curve up into a lot of really small rectangles, and then adding up all those really small rectangles in the appropriate way based on kind of the area that we compute across all these really small rectangles. Because this isn't an analytical derivation, there's an error associated with it, because it's a numerical approximation of kind of an integral defined over some domain. It could be that this function that we were integrating is like really weird and spiky, and that even if you get really close with these slices, maybe the function shoots up really high in some really hard to define way. In that case, the integration error might be a lot bigger. But in this case, the integration error is pretty small, because we're working with the normal distribution, aka bell curve, aka Gaussian, and that's why the error here is pretty small. You can always make your error better and better by making the slices that you're working with better and better too. So the basic idea behind the slices is you turn this continuous thing into something discrete, and then you do just what you would do in the discrete case, but you have some error associated with it. So that's just intuition for that. Does that make any questions, follow-ups? Yeah, very good. Other questions? Yeah.
So like, why would I want to use method 1 or method 2 when I can just calculate the CDF the other way?
You mean using the built-in functions?
Yeah. So like, what is like the purpose between doing method 1 and method 2? Is it just different ways to do the same thing?
Yeah, good question. So for those of you on the recording, the question is, why would we ever do this, method 1 versus method 2? Why would we ever manually integrate versus just using the built-in functions? So the first answer I would say is the built-in functions are usually going to be optimized. Usually someone has written them in a pretty fast manner. So in general, I would stick to the built-in functions. The main purpose for introducing method 1 is so that you can see it for yourself what's actually happening, because we're not going to spend a ton of time in this class doing integrals by hand. I know you might be sad about that, but I figure we need to get other material. We need to get you to the research side of things, and you can take classes on that if you want to. So we're not going to push that super hard. So instead of doing that, we're showing you this integration, in a numerical manner, just so that you can see what's happening. So that's the first thing I'd say. The second thing I'd say is, in some cases, you might be working with a complicated research problem where no one's ever worked with the distribution before, and there's no, in a sense, pre-built formula. In that case, you might need to rely on integration, so these manual integration functions. So for example, we have, if you go to PaulMeth, you might hear of people constructing these Bayesian methods for this, these Bayesian methods for that, and some of the approaches that they're doing actually will use methods very much like this, where they can't actually get the closed form, or they can't actually use a built-in function. They have to do this, manual numerical integration to try to get what they're getting. So this would be another setting where you would use it. Good question. Other questions? I heard in the back there might have been some questions in the back, but any questions? Are you good? Okay, a question in the back was resolved. Very good. Okay, so that's that. And like I said, they always would say, don't just think something one way, learn it multiple ways, 2 ways, 3 ways, 4 ways, 5 ways, and then you'll see the interconnectedness between all the different ways, and you'll understand it more deeply, and that'll be really good. So that's that. It's about 1:23 for those of you, yeah, and we have about, we'll go through this in about 10 more minutes, then we'll do maybe an earlier break, and we'll come back together after we're done with this. So then method 2, this is just the other method. Okay, so we have this. What is this doing? I think this is a little bit old. So the basic idea behind this is, so the basic idea behind this is how you find the probability of falling between any two numbers. So this would be like the probability that 0.99 is less than x is less than or equal to 2. That's what this calculation is doing here. We're finding that probability. So x, remember, x is a random variable. So it takes some getting used to. I'm hitting this home again because it's good to hit it home again. X in this sort of formula, or I guess equation, or whatever you want to call it, x is a random variable. It's something stochastic. It's something that we don't know exactly what it is. So we're basically saying, what's the probability that x falls within this little interval? And we can use p norm to compute that. And this is going to be really important. And this is basically doing, it's finding the area within this curve like this. So that's what's happening there. And just one other note, I think we even do this later on, but you could use integrate to figure this, to compute the exact same thing. But instead of the lower bound being negative infinity here, the lower bound would be 1.99. So this should just give us the exact same answers what we get here. We're sort of doing the integration directly from kind of from here to here, instead of integrating to get this area, this full area, and then subtracting off kind of the full area there. If you can kind of visualize it, it's good to try to think visually. So what's being subtracted, what areas are here, what areas are there, and just come back to the visualizations, and I think the story will become clear. So that's that, and so forth and so on. So now this is the integrate way, this is the p-norm way, this is the integrate way. So I have a few examples here. Hopefully it seems like from the questions that it's getting, I hope, clear. But before we go on, there's one important thing that we should cover, and that's this notion of a quantile. So I'm introducing one other concept, which is going to be important as well for probability, for statistical inference. So remember how we had p-norm, and we know what p-norm is doing. We know what a cumulative distribution function is doing pretty well. And you've also thought a little bit probably in the past about like a quantile. So maybe when you took the GRE, you were in the 99th quantile. I'm sure all of you here were in the 99th quantile, and that's why you're here, because you're great students. So you might ask yourself, like, what score would I need to get to be in the top percentile of students? Like before the ACT, I might want to know, how can I get 100% in the hundreds? How can I get better than every other student? What score would I need to get to actually be in the top? This is a natural question that you might ask, and it's also a question that you might ask in statistical modeling too. In my statistical model, what just in intuitive sense, not very formal, but what value of what kind of effect do I need to estimate for that effect to be significant in some way? So there are all these questions of like what do I need to get to have a certain probability associated with it, and the cumulative distribution function answers that. So it's basically, to use the lingo, the inverse of the CDF. So the CDF tells us, so here, line 89, what's the probability, given the distribution defined with these parameters, of seeing something 0.9 or below. That's what this is giving us. So it's giving us a probability. And now we might ask, what value does the random variable need to take on to have 75% of all observations below it? So let's just write that out. What value does x need to take on so that 75% of observations are I guess let's just say below it, and you know what that means? It means like it means less than or equal to. So we can use the q norm function for doing that. So the input to p norm is q, and the input to q norm is p. And that's just a way of remembering that Q norm is, in a sense, the inverse of P norm. And maybe some of you haven't taken the inverse class yet, but inverses just mean you do the thing and it gives you back. If you apply a function and then you apply the inverse of that function, you get back the original input. So in this case, the two functions sort of work in tandem. So Q norm basically answers the question, what percentage of my data, what value would my random variable need to take on so that 75% of my data are, below that value. So in this case, when I hit Q norm, it gives me that. But I could, let's just for the sake of experiment, let's just, what value would the random variable need to take on so that value would be greater than 0.9999 fraction of the data, so to speak. And so if line 93 gives me 0.9, can someone tell me something about when I hit enter what is going to happen? So now I made P bigger. What do I know? What are some of the properties that P that the output here is going to have? Well, I guess I already did it. So sorry. But because we're looking at a higher probability, the value that the random variable needs to take on to get to that higher probability is bigger. So in other words, if we have this bell curve, this quintessential bell curve, and you could use this with other distributions too, with the Poisson, with the gamma, with the beta, with all these other distributions. But when we're working with the cumulative distribution function, we're basically saying I'm interested in the value of x such that 99% of the area, so to speak, or 0.99 fraction of the area to the left of it is encompassed. So in this case, as I move this threshold out to the right, the value gets bigger and bigger and bigger, and the area encompassed gets bigger and bigger and bigger. So that's how you know that when I make P bigger and bigger and bigger, the quantile is going to be bigger and bigger and bigger too, because you're sort of pushing it out towards the right-hand side in some intuitive sense. So maybe just as a review question, let's just ask this. So maybe with the person sitting next to you, what happens if P were 1.2? Just talk about that, or maybe think it through, maybe silently as well. If P is 0.12, what does that mean? Is that defined? Is that well defined? Is that not well defined? What are your thoughts? Does anyone want to take a crack at that? What would be the interpretation, and why might that be something that we wouldn't want to do, or might want to do, or what are your thoughts? Yeah, so in this case, if P was 1.2, we would basically be asking what value does X need to take on so that 120% of the observations, on a resampling basis would be below it. So this wouldn't really be defined. It might give you something, but I think it most likely will just give you an NA, because once you get to 1 in probability, you can't get any higher. So if you were going to ask yourself what percent of observation, what value does X need to take on to be below, it's not well defined, because probabilities have to be bounded between 0 and 1. Because of that fact, the quantile distribution function is only defined between 0 and 1 too. Since the input to the cumulative distribution function, it has to, or the input to the input to this function has to be between 0 and 1. So when we give it something outside of those domains, it doesn't know what to do. It gives an NA. And the interpretation of that would be, we're asking what would be the value of X that gives us a negative probability. And that's not really well defined. There's no value of X that would give me a negative probability. So as a result, when I give the Q norm function a negative number, or when I give it a number above 1, it's going to give me an NA, because it's just not well defined. There's no probability above 1, and there's no probability below 0. So if I ask, what value does it need to take on to be below 1 or above, below 0 or above 1 in probability, it's just not well defined. So that's just a subtlety there. Explain that. Are there follow-ups to that? What are your thoughts?
Can you also explain the P norm in the way that you just explained?
This one up here, P norm? Yeah, so P norm, that's a good question. So the question is, explain P norm kind of using the same ideas that we just talked about. So that's my prompt as if I was ChatGPT. So P norm, we have this, so the thing on the right hand side, mean equals 0.2, standard deviation equals 1. That just defines the distribution. So there's that. So we don't really need to think too much about that. But what we do need to think about is this Q part. So P norm is the, it gives us values from the cumulative distribution function. In other words, like what's the probability that the random variable takes on a value as like Q or below. So here they just what we've been using as X, they kind of use Q in a certain sense. So it's just notation really. So the answer that we get in this case is 0.758. So the idea here is that if we were to repeatedly sample from this distribution, if we were to take random draws from this distribution, about 76% of all of those random draws would be below 0.9, would be 0.9 or below, kind of in that sense. So it's computing a probability, and it's giving us that. And we can think about the bounds of what Q can be. So in this case, Q can actually be any number. It can be any number at all because this distribution is defined over the continuous real number line. So it can be negative. It could be a negative number. It could be a positive number. It could be a real number. It could be it's defined over the entire real line. So as a result, Q could be negative. It could be negative 100, and it might give us a really small value. Like let's do negative 2. It's still well defined. It's just maybe a little bit smaller based on the shape of the distribution. And Q also could be a really big number too. So Q could be 10. Q could be 100. That's just basically saying we're basically just asking on the basis of that. The probability, we're asking ourselves a probability statement about the random variable x being less than or equal to q. In this case, I can insert in any value for q. I can insert in any sort of value at all, and it's still going to give me an answer because in this case, even if q is a really, really big number, it's just kind of above where the distribution is centered, or it could be really, really far below where the distribution is centered. And in those cases, the probability of seeing something kind of Q or less is either going to be 0 or 1 in those two cases. Does that explain, or try again? Or maybe someone in the audience or someone in the room has another explanation that they want to share.
Yeah, so the Q here is basically a value of one time.
Yeah, it's a value. It's a kind of a hypothetical value that the distribution could take on, and we're asking ourselves, what's the probability that the random variable is kind of Q or below? Yeah, good question. This stuff can get a little, thoughts?
So, could you you were talking about the GRE and the quintiles?
Yeah.
So could you use an example like that to explain what's happening with the p-norm function?
Yeah, good question. So the question is, can we use this GRE example or something like that to explain the p-norm function? And the answer is, so in that case, so Q would be the score. So let's just say that the test makers have standardized the test results so that the test scores have a mean of 0 and a standard deviation of 1. Standardization basically means you subtract off the mean and you divide by the standard deviation. And if you do that, you get something that then has a mean of 0 and a standard deviation of 1. We'll go through that later on in the course. But let's just assume that for the sake of argument. So now, if we could generate synthetic test scores using that distribution by going, test scores synthetic, and we could say R norm, 1,000, mean equals 0, standard deviation equals 1. So in that case, I've generated all these synthetic test scores, and some of them are, negative, some of them are positive. If the value is negative, that means that person scored below the mean. If the value is positive, that means they scored above the mean. And we can also look at a histogram of all the different results, and they look sort of like this. And in the context of the test score, we might want to know, my test score was a 2. What percentage of students am I above? Am I scoring above 10% of students? Or am I scoring above 90% of students? So that question can be answered using a Q-norm function. The Q-norm function answers that very question. So in this case, this line 99 would basically say, what percentage of students am I scoring higher than if I get a 10 on the test, a 10 on that standardized scale. If I get a 10 on that standardized scale, then I'm scoring higher than essentially all of the students who took the test. So this is the histogram, and if I score a 10, I'm way off that histogram, way over here, and I'm just really doing a lot better than all of those other students. If you so this number, this 1, it's not exactly 1. There's a certain rounding error associated with this because we're working with we're working with the normal distribution. And there's actually kind of a tail here on the right-hand side that goes on and on and on and on. It might get really small, but there's always a non-zero probability of getting any value because it's because of how the distribution is structured. So technically, this 1 is not really a 1. It's like a 0.9999999. And my computer only has a certain amount of kind of ability to represent numbers, so they just, in a sense, round it to 1. But that's just a subtle point to keep in mind. Technically, it's a really kind of, we're greater than almost all in terms of, if we were just to take that integral, but there's a little bit of probability that we could get even higher. There's a little bit of probability that we could get even higher, no matter what number we chose. But that probability is vanishingly small. Good question. Other questions, other comments? All right, I don't see anything for now, so I'm going to move on. Here's some more practice, giving you experience with Q norm and P norm, and doing some of those negative numbers to see what would happen. So that's that, and we're almost ready for a breather, like a mental reset. But we have one more thing to do before we do the mental reset, and that's just to talk a little bit about conditional probability, which we're going to talk about again today. Because as social scientists, we don't care that much about the overall rate of support for this candidate or that candidate. We often care about breaking it down by, let's say, ethnic lines or gender lines or age. Do younger people generally support one party or another party? Do older people generally support one party or another party? That's all related to conditional probability, which is what we're going to talk about later today, hopefully in an engaging manner. But the one thing I will say, just to try to get an intuition for this, is that you can use the simulation-based methods that we were also talking about before to gain some intuition for what conditional probability is doing. So this first thing is basically me reminding everyone how you can use random numbers to calculate probabilities. So what we're doing in line 123 is we're basically drawing a lot of random numbers from a specific distribution. It's a Poisson distribution. There's a specific lambda parameter associated with it, and that gives us these x's. Remember, the Poisson distribution is defined over counts. So if you're studying Civil War, you're going to be potentially using the Poisson. If you're studying number of protest events, you may potentially be using the Poisson. But here we're using it too, and we can generate these random draws, and we can actually calculate the approximate probability that x is less than or equal to 1 using the fact that probabilities can usually be thought of as the expectation of an indicator function. That's just a fancy way of saying I can do this line 124, and this calculation in line 124 is going to give me something like a probability. So P plus is like, what's the probability that this Poisson distribution takes on the value of 1 or less, given the fact that lambda is equal to 3 in this case. So this is giving me it's giving me a probability, and I could calculate that same probability, at least approximately, using some of the methods that we've been talking about, where we're using the simulation-based approach to say, I have all these draws from this distribution, so I can just use them to approximate the probability by basically saying what fraction of observations are less than or equal to 1. And this is a way of approximating that probability. And that's that. That's kind of a little bit of a review, but if it feels new, that's fine too, because it's new. Maybe this is new perspective on it. So that's what we would call marginal probability. But we also were talking about something called conditional probability. So now we're going to do an example of where we calculate using R a conditional probability distribution using the random numbers that we get from these. So now let's say we have a random variable x, and let's say we have a random variable y. How we generate them is not super important for right now, but here are the instructions for how you do so. Now we get this random variable z. Z is the product of x and y, and z, we might think about like what's the expected value of z given this complex set of conditions there on the right. And we can, again, one of the beautiful things about simulation-based approaches is that you can use these random numbers to calculate an approximation for that more complex thing. Like we could do the analytical formula, but it might be complex. It might take us a while. In R, we can get a first stab at it. We can get an approximation, what's known as a Monte Carlo approximation, really straightforwardly, really easily. We're just with this because we're subsetting the z data based on this condition of the other data, of the x and of the y data. And when we subset the data in that fashion, we can then get, these are basically draws from that new distribution which has that special condition, and now we just take the mean of all those draws, so to speak, and that gives us the expectation. So there's a little bit of lingo there. I'm using the lingo from kind of probability theory. Hopefully you're able to follow it. If it doesn't make sense, let's ask questions, let's get comments, let's ask your peer. But now, before we go into the next part of the course for today, let's just see like how we would calculate the conditional distribution of z based on those conditions. So this is a condition that x is greater than 1 and y is less than 10. So we have this complex condition set, and can we approximate the PMF in that case, the conditional probability function in that case? So we're trying to get this, and the answer is yes. And we can go back to if we go back to deep in the past, a few weeks ago we talked about that table function, and we can actually use the table function again. So what we're going to do here is we're going to subset the the z data on the basis of that condition. That's what we're doing there in what's highlighted. And then what we're doing here in this next thing is we're basically saying we're counting up how many values of z take on all those different possibilities. And then when we have the prop.table command, we're basically normalizing everything so that the overall sum across all possibilities is equal to 1. And then we're plotting this here. So this is a way to approximate that complex conditional probability function on the basis of these random draws from the distribution. This is very similar to what you would do. Let's say that you worked for the census. And let's say that you got data on, let's say you had the raw data on, gender and ethnicity and age. And you wanted to understand what is the probability that someone lives in a big city versus a small town on the basis of different age and gender and ethnicity subgroups. You would basically just tabulate the data, and then you would normalize, and that would give you the probability. We're doing the exact same thing here now with these simulated data, and this subsetting operation is giving us, is sort of our way of specifying the condition, and then we're plotting it so that we can kind of see what's more likely and what's less likely. So I have some thought questions here. You can think a little bit about those. We could also, use Bayes' rule to calculate this too, but in this case, we didn't need to use Bayes' rule because we had access to all of the different distributions. We had access to the x, we had access to the y, and we had access to the z. This is known as the conditional we had access to that conditional draws from that conditional distribution, and because we had draws from that what's known as conditional distribution, we were able to calculate it using the tabulation approach. In other approaches, you might not have draws from the full, I should have said joint distribution. I'm not sure if I did, but we might not have draws from that full joint distribution, and we might need to use some of those tricks of the trade known as Bayes' rule. Those ways of using something other than kind of the full probability distribution of everything to try to compute probabilities. So we're going to talk a little bit about that, and we're going to go back to that Civil War example. We're going to talk about it. We're going to go through that example again, and we're going to go through some other things again too. So let's take a 4-minute break, and then we'll come back together.
It's
talked about this stuff. Do you think anything we should rehash? Anything we should cover again? Or?
Many voters expected that the male candidate would be nominated.
Yeah, this conditional stuff is
Female
kind of
candidate was
hard.
nominated, and they ran an experiment. That's why I went.
It's a little bit fine,
They wanted to learn about the person that she didn't
but
anything else.
it's good that
Maybe I'll talk a little bit more about the results rehash it.
or maybe next
And they,
Okay,
or I
that's
can
good.
or I can do some
but they were not
CA
satisfied.
sessions.
So they
You might feel like
ran an
being
experiment.
that horse.
Generic female and
That's
male
interesting.
candidates
I kind of want to play around with it. I don't think we've
So
seen it before.
their result is that
Usually people just do it by hand.
oh, I think online.
But yeah, I think what I should have done in retrospect is what I should have done is plotted the marginal distributions of X and Y and Z, and then the conditional. That would probably be better.
But I think their experiment made it some kind of
It's tough.
sophisticated
Often you only know factors.
that examines the effects.
What is the requirement? What is the requirement? Is it
Well, I think so. X has to be greater than 1, and Y could be less than 10.
variance in lambda?
Oh yeah. So
Is lambda on X like high or something?
no. It's exactly 0. That probability of 1 is exactly 0. I think. I think that's because if X has to be greater than 1, then yeah, it's gonna be this like 1. It has to be.
There's not an intersection at all.
Yeah.
Quick question.
Yeah.
Any reason why they saved
Yeah, it could have just been 3 there. I just wanted to give people another exposure to saving things in the definition of the arguments of the function.
Okay.
Yeah, good question. And it doesn't have to be underscore either. I just like to keep everything underscore
Okay.
to avoid confuse myself. Yeah, great question. Jack's now for everyone. Doesn't work particularly well. There are some bugs, but hopefully they fix it.
I've used it a couple of times. Works well on that machine. It's a piece of this on one sheet. It's the other one.
Yeah, no, it does.
I prefer it when it's on stuff.
Yeah, I think I'm gonna retire from this book. In the future, we'll just teach either Jack. Yeah, exactly. Alright, we'll come back together. So this is a question for everyone. I think, well, last year I remember the students were saying we need to end 15 minutes early for some reason. Are your other classes ending 15 minutes early? Like relative to the time they say they're ending? Should we do that too?
No, but it's gonna be 30 minutes in this class, right?
We could, well, for today it would be, but that's okay. So we could do 10 minutes. Should we end 10 minutes? I mean, I just totally forgot about that. They don't really remind us about these things. So unless you remind me, I'm going to forget about it. Since it's so weird, they say the class is, an hour and 30 minutes, but then it's not an hour and 30 minutes. So we can, why don't we end we could end at like 10 minutes before it was supposed to, if that makes sense. I'm not sure. We could have a vote on it too. 10 minutes before?
Yeah.
I mean, people, I think we get tired. I mean, it's an hour and 30 minutes is a long time, and your time is valuable. So we'll do 10 minutes. So if I keep going, just remind me, raise your hand, or just start walking out, and I'll hopefully get the message. Another thought we have, first of all, on the piazza, we have a little vote for future class offerings. This is for spring of 2025, so by that time, we'll all be a little bit older, a little bit wiser, so to speak, but hopefully wiser too. So it's still loading. But so on the piazza, while it's loading, I'll tell you what we're going to see. Basically, there's a chance for you to vote for what class you want. I might be offering both these classes. I still have to negotiate it with the people in power, but this is a poll. We'll definitely be doing the big data course since that seems to be winning right now. But if you really if you want to do the machine learning course, just keep voting and hopefully we'll figure out something. But right now, the big data course is winning in this race.
If you want to do the machine learning course, we'll punch the data for you.
Wow, you fudged the data. Okay.
So you have bargaining power to do both of them.
That's true. That's a good point. So I will. I'll.
It's all a scam anyways.
Yeah. Well, it is what it is what I would say. So I'll let you know what the conclusion of this would be. But right now, we'll definitely plan on offering the making big data. In the machine learning one, it'll be a question. It'll be. We'll have to discuss about it. But we might still offer it too. So stay posted on that or stay tuned on that. Otherwise, I think people are using the Piazza, and that's good. And I won't go through the Piazza too much just because we have a few less minutes than I thought we would. We won't talk about the terminal. I'll just show you the terminal, which is what we talk about the terminal in the Making Big Data course. So I'll just show it to you now so that you have it in the back of your minds now. And then later on, we'll talk more about it in the Making Big Data class. That'll be all of us together there. So we had some thoughts about, things we can do to tweak this for next time. But before we talk about that, let's just go through some of the materials for today. So this is kind of reviewing material that can be somewhat challenging. So remember how last time we introduced this example of the CIA predicting when civil wars will happen, and in that case, it's right 85% of the time that it predicts it's going to happen. It happens, and it predicts civil war in 2% of cases. Civil wars happen in about 4% of cases. What's the probability that, given a civil war actually happened, it was predicted? This is like a mind-bending question. If we didn't have rules, if we didn't have guides who came before us who thought really hard about these things, this might be a challenging question to compute. And in fact, Aristotle or Plato or, the people who invented algebra thousands of years ago, they didn't really know what the answer to a question like this was. It was something that came later. This is an answer to a question like this is a relatively recent phenomenon. So if it seems like a mind bender to you, that's because it was a mind bender to the ancients as well. And here's the answer that we talked about. The probability that given a civil war happened, so H has happened, the event that happened, that it was predicted, this probability, it's only about 0.425. So the intuition is when a civil war is predicted, it's happened more often than not, but it doesn't predict civil war in many cases. So because of the fact that the CIA misses some civil wars, the probability that given that the civil war happened, it was actually predicted, this probability is much lower than the probability that it's correct when it predicts civil war. So another way of saying that is this example shows you how if you only predict confidently in cases where you're confident, the signal to noise ratio still might not be great because you're missing cases when there will be civil war. You're not predicting those cases. When you're not confident, you're not predicting them. So this is just an example of using Bayes' rule in practice and how it can be a bit of a mind bender, and it's a motivation for making explicit these rules of probability, these rules of later on statistical inference, and then even after that rules of other kinds of inference as well. So this is just the example that we talked about last time, and we talked also about these different varieties, if you will, of conditional probability. The example from the R session today shows you how the conditional probability distribution is a probability distribution like any other. So if we just go back to this, example here, this probability distribution it's a legitimate probability distribution. It says the probability of that this new random variable takes on these different values. It's a distribution just like any other distribution, but it's defined over this set of conditions, if you will. So this is just giving you a sense that conditional probability is still probability. It's nothing more fancy than that. So this is this principle here. Conditional probability is still probability, and that's just one clarification there. So, this is just we talked a little bit about this. We also talked a little bit about this way of representing probability as area, and then how we can think of Bayes' rule as basically restricting ourselves to this subset of events, defined here by B, and then we're looking at this intersection area, and then we're renormalizing. That's what we talked about last time. We could talk about it again too. We also have the videos if you want to see the videos. Another thing that I didn't mention last time, but that's important to mention, is that if two events are independent, then the probability of one event given the other event is just equal to the original probability. So in other words, we have A and we have B. So in this case, I think like A in the previous slide was Bush wins re-election, and B was the Pope resigns. We might have a baseline answer as to what's the probability that Bush wins re-election. Let's just say it's 0.7. The probability that Bush wins re-election is 0.7. If we also then knew that the Pope resigned, that's what that B would be. If we knew that the Pope resigned, we might not think there's a very strong link between those two things. That's kind of a random example. Those are weird events. They're not really related to each other. So if I thought that there wasn't at all a connection between A and B, and in fact, if these two events were what's called independent from each other, then the probability of A given B would just be the probability of A. In other words, knowledge of the Pope resigning doesn't change our guesstimate for the probability that George Bush wins re-election. So this is intuition behind statistical independence. Question, comment?
Why is the probability deferred to A and not to B?
Yeah, good question. So the question is, why is the probability of A given B not B? And the answer is that in this case, we're kind of holding B fixed. We're assuming that B is known. So we're looking at the only uncertain thing here is A. Yeah, B is not known, or B is fixed, A is not fixed. So that's why we do that. But at the same time, if we just flip these two things around, the probability of B given A would also just be the probability of B. So it works both ways if these two things are truly independent from each other. In other words, independence is a symmetrical relationship. In other words, if I don't know the Queen of England doesn't know me. It's kind of the intuition. We have to know each other. There's a symmetrical relationship between the two. So this is the definition of conditional probability. You can use what's known as the chain rule for probability to reformulate, refashion, reframe the Bayes rule from this first thing up here on the first line to the second thing on the second line. This second thing on the second line is more of a canonical formulation. It's what you see on all the T-shirts. It's what you see everywhere. It's more of a kind of popular way of writing things. And the question is why? Why is it more popular? And the answer is that this way of writing it up here on the first line, it's really nice. It's really elegant. I really like that visualization that we talked about last time. But the problem is what's known as the joint distribution up top. That's like the probability that the Pope resigns and the probability that Bush wins re-election. That might be really hard for me to know. I might not know the probability of both things happening, so to speak, or the joint distribution over them. But I might be able to break things down into these smaller subcomponents. And the basic intuition here is that I want to know the probability of A given B. So I want to know the probability that someone votes for a Democratic candidate given their age and maybe ethnic profile. That's what I want to know, but I might not be able to observe that directly. Maybe I would be able to observe directly the reverse, like the probability that of their age and race given that they vote a certain way in some situations. I guess you see what I'm saying. One of these things might be really hard to know. The other thing might be really easy to know. In general, these marginal distributions with social science data can often be easy to know. Like, for example, this marginal distribution is just like it could be like the marginal distribution of women, or the marginal distribution of men in the population, or the marginal distribution of different ethnic groups. And I'm interested in the conditional distribution of voting on the basis of those subgroups, on the basis of race, on the basis of gender, and so on and so forth. So that's through the magic power of Bayes' rule. The magic power of Bayes' rule is it lets you basically use something that might be hard to compute. It lets you compute it using something that might be easier to compute. What exactly that would look like for your research question will be subject dependent. So in other words, what's easy to compute and what's hard to compute, this might be subject to the data that you have available to you as a scholar, as a researcher, as someone studying some of these things. So that's just what I would say there. This is just refreshing, reviewing, reformulating conditional probability, and just illustrating how there are really two formulations of Bayes' rule. The first one uses the joint distribution, don't forget joint. The second one uses the chain rule, which is a way of decomposing the joint distribution. And this is just another way of writing the chain rule for probability. One note here for those who are looking at the board, the probability of A and B can be written also with commas. So sometimes you'll see this intersection symbol. Sometimes you'll see this comma symbol. They might have slightly different connotations. The connotations for right now the nuances aren't super important to get down. So just know that there are multiple ways of expressing this sort of joint distribution idea. And that's what we have there. And this looks sort of complicated. Like the probability of A and B also equal to the probability of A intersect B. It's equal to the probability of A given B times probability of B. That equals probability of B given A times probability of A. It looks a little bit abstract, but we can break it down extremely simply with a certain example. The basic idea here is that the probability of a recession today and the probability of recession yesterday is equal to the probability of a recession today given the probability of recession yesterday times the probability of a recession yesterday. So there's a certain sense in which you can kind of unravel probabilities. This sort of thinking gets used a lot in time series analysis. Maybe you're going to go on and take a time series analysis course either in the stat department or the gov department or the CS department or the economics department, and you'll use this chain rule a lot because you'll be doing this sort of breaking down of some joint complicated thing into these these conditionals and marginals. So I don't really have a better intuition for you there. It's sort of, you can drive this from Bayes' rule. Maybe next time we'll go through maybe derivation. But the basic idea is that I tried to write it out here. If A or B does occur, basically things inform, if one thing happens, that informs you about the other thing that's going to happen. And then if you reweight the thing that happened by its probability, you get a distribution over the joint between the two things. That's kind of an abstract way of saying it, but just think about this example of recessions, or maybe Andres during the TA sessions. I'm sure we'll have even better examples for you there. But that's just an illustration of the chain rule for probability. And now we only have about 10 precious minutes left because they're taking away our time for some obscure policy that I never got informed about. But there are other implications of conditional probability, and I feel like I'm kind of droning on, so I'll try to keep it lively. But there's one thing that's really important, and that's called the law of total probability. We're just sort of listing rules and listing it's a bit of a list today, so next time we'll get into some more exciting things. We'll talk about variance, we'll talk about uncertainty, we'll talk about the stuff that we all want to talk about. But we do need to talk about the law of total probability, and that's basically a recipe book for getting the probability of something happening overall using all the different possible ways that could happen. So let's just use an example first, since we're always in this class now trying to start with the examples and then go to the general thing. And the example is, like, what's the overall probability that Biden wins in 2024? Well, you can think about that as the weighted, as the sum of the probability that he wins against Trump, weighted by its probability, plus the probability that he wins against DeSantis, adjusting for the probability that DeSantis is the contender on the other side, plus the probability of all the other candidates, weighted by their appropriate probability. So in other words, the overall probability that Biden wins is equal to the probability that he wins against each of the candidates that he could compete against weighted by the probability that he competes against those candidates. Does that make sense to people? You're sort of saying Biden's going to win against Trump with, I think right now in the odds it's like 56% chance. So there's a 56% chance he wins against Trump, but Trump may or may not be the candidate on the other side. It could be someone else. So you have to take that, 0.56 and then multiply it by the probability that it's Trump on the other side. And I think it's like 69 probability 0.69 that it's Trump for the for the GOP candidate. So you then rebalance by that. And then you do the same thing with DeSantis, and you do the same thing with all the other candidates. You would just say the probability that Biden wins against DeSantis, I think it's a bit higher. It's like probably 0.7. And then you'd reweight by the probability that DeSantis competes, or sorry, that Biden competes against DeSantis. So you just reweight things in that way. So these are just different formulations of that same idea. I really like formulation 2. So you're basically saying the probability of A, which here is the probability that Biden wins, is just equal to the sum over all candidates. So now here, think of X as being all the different candidates. So curly X is the set of all candidates, and then little x is a specific candidate. And then you basically just say, the probability that Biden wins given Trump times the probability of Trump. And then you would, sum up over all the different possibilities. So you're weighting by the marginal probability of x, and you're then taking the conditional probability of A given x, and this is known as kind of averaging over x or integrating out x. There are different ways of saying it, but the idea is very simple, very intuitive. You're just basically saying it could be all these different things. So let's compute the probability that Biden wins given all those different things, and then weight by all the probabilities of those different things happening. So that's a recipe book, if you will, for computing the probability that something happens overall. And this gets used a lot in those models of probability, whether it be in the betting markets or whether it be in the context of a public poll, public opinion polling, or all these other different things. You can kind of reconstruct something overall from something that's this is basically saying you can reconstruct the overall analysis from the subgroup analysis. Any questions about that? And just on the bottom here, this bottom equation, this is basically just saying you can also condition on some other event C, and the same thing holds. In other words, the probability that Biden wins, given he's the nominee, equals the probability he wins. You can always just condition on that event C, and the whole thing goes through. It's sort of the lingo of it. So that's what equation 3 is saying. We have about 8 minutes left. I think 8 minutes. So this is just to reiterate, this is the law of total probability, and you can write it in many different ways. I've written 3 or 4 ways here, whether you're partitioning things or whether you're using other random variables or whether you're using extra conditioning set. This is just different ways of saying the same thing. The intuition is listed out here with this example with Biden, but hopefully you're getting some experience now thinking in terms of calculating the overall likelihood using the conditional information. Okay, so now we have a few different things. This is just an example. I probably won't go through this. Basically, you can use Bayes' rule with not just 2 conditioning events, but actually 3 conditioning events, and you can basically always just condition on that 3rd conditioning event, and it goes through all the same. So that's a bit of jargon for you, but that's just basically saying if you want to know the probability of one thing using multiple sources of information, this is another recipe book for telling you how you perform that analysis, how you average all that, how you integrate all that information together. If you know 2 things and want to calculate the probability of the 3rd thing, this is a recipe for doing it, and it's basically the same as what we had before, but we're just always conditioning on that C here. There are other ways of doing this, but this is one way. Okay, that's that. This is just, and I have some examples here, like what's the probability of different incomes given age and race? In that case, age might be B and race might be C. Or we might ask ourselves, what's the probability of a null hypothesis being true given our data and also given a specific model class? That would be like something from statistical inference, which we'll go through now. And you might go through in other courses as well, Stat 1, Stat 2, in Stat Department courses. So these are some other implications for conditional probability. And in the last thing here, I have this here really just for your own edification, or it's just interesting. The importance of conditional probability. This example, you can look through it, but basically this statement's really complicated, but the basic idea is really simple. The basic idea is sometimes conditional probabilities imply one thing, but marginal probabilities imply another thing. So there's a famous example. This is called Simpson's paradox. I'm not going to really belabor the point too much with this because the practical implications aren't, for the kind of statistical modeling that you're going to do, not super strong. I mean, I think there are practical implications, but for the kind of things you'll do, probably it's not going to come up a lot. But the basic idea behind Simpson's paradox, I have it written out, a little bit more formally here, but we can just use an example to illustrate it even more quickly. And this is the famous example from this lawsuit with UC Berkeley. And the overall admissions rate to their graduate program was higher for men than it was for women. And there was a lawsuit, and the data was all aggregated together. And then they found through this lawsuit that if you look at any individual department, there didn't seem to be a big discrepancy. So the idea here was that conditionally, marginally, the admissions rate for men was a lot higher, whereas conditionally, it seemed about balanced. And people were wondering, why is that? And the answer is that basically how the conditional probabilities get weighted together matters a lot. In other words, the women generally were applying to harder to get into departments, which led to the overall discrepancy, even though, at least in this example, marginally there was a big difference. Conditionally, there wasn't a big difference. And this just shows how the marginal weights in this law of total probability determine how the conditional information aggregates. So even if you look marginally, you might find one thing, but conditionally you might find another. On the basis, and it will depend a lot on how that conditional information aggregates together using those weights, these kind of marginal weights on these B's, if that makes sense. So this is just one example here of how the law of total probability can be used to kind of break down something complicated into something simpler. Like, it's really, like, how are we supposed to analyze this? Well, one way is to break it down by subgroup. So look within subgroup, and then you'll get an understanding of the reasons why you either see or don't see a discrepancy. Is it because of this reason, or is it because of that reason at the level of the aggregate data? And this is one way of breaking it down using at least the observed data that we have. And there are other ways of trying to get at unobserved sorts of things. Like, for example, what about unobserved factors that we can't see? How do those matter? There's literature on using sensitivity analysis to try to piece those things together, but this isn't really a course on that. And the basic idea here is that probability can be subtle, so it's important to think about it, from the first principles, which is what we're doing with the things that we're learning, all of us together now. So that's one application, and in the last 3 minutes, we'll just briefly introduce you to this notion of statistical inference, and we'll briefly introduce you to this notion of likelihood and prior probabilities and other things like that. So the basic idea here, and I'll just flip through it to get to the upshot. The basic idea here is that we often have data. For example, data on political leaders from across the world or from a historical context. So Andres is doing a cool project looking back in time. So we might have all this data on historical leaders, and we might want to somehow model that data. Well, we're going to model it in the material that's to come. We might model it using these parameters that are known. Well, here we're just going to call them thetas. Remember how in the Poisson distribution we had lambda. Lambda was a parameter. In the Bernoulli distribution we had p. P was a parameter. In the normal distribution we had mu and we had sigma squared. Those were two parameters. So we have different distributions, and those distributions have different parameters. So when we're trying to model our data on all these leaders going back thousands of years, extensively exhaustive, we have we have some assumptions of how those leaders are distributed, or we might have some assumptions on how their characteristics are distributed. And that theta, it's not something we know for sure. That theta is something that we're going to try to use the data to learn about. So something that we're going to learn about in the second half of the course is these following two things. The first thing is P of theta given D. This is the conditional distribution of the parameters given all the data that I actually observed. This seems important because we're basically saying what values of, let's say, lambda, or what values of mu, or what values of these parameters are likely and what values are not likely given all the data that I actually observed. The framework or paradigm for learning about this quantity is known as Bayesian inference. There's another framework or paradigm called MLE, which is something that you'll learn even more about in Stat 1, Stat 2, other courses, and that's kind of the reverse thing, the probability of the data given the parameters. And these are two things that we'll learn a little bit about in what's to come. And the basic idea is that you can actually use both of these to perform inference on your data. And actually, with more and more data, these two things can lead to more and more similar conclusions. So here's an example that I listed out here, but the basic idea is we want to model our data on leaders going back to the earliest recorded moments of history, and we have some distributional kind of structure imposed on that. We have some parameters that are called thetas that kind of govern that structure, and we're going to think of how we can use Bayes' rule, how we can use other approaches towards learning about these conditional distributions so that we can better model our data, so that we can better learn about the social world, so that we can better make inferences about what we should do to try to improve it. So those are a few thoughts for you today. We're going to end 10 minutes early and I hope you enjoyed it. We'll come back together next Wednesday, or this coming Wednesday, and we'll talk more. So thank you all.